Okay, so this is the first, I think, of two videos I wanted you to look at about alternating series. And the thing about an alternating series, it's going to alternate from positive to negative. And one of the hallmarks of an alternating series is a power of -1. So that's probably the easiest way to make it alternate, although there are other ways, which we'll see. But anytime you see that, right, that -1 to the n, so that you're just going back and forth in positive and negative values. Now, like we've kind of seen a couple of examples where, if you have something that's alternating, positive, negative, but the behavior starts to get closer and closer to the, like, maybe on both sides of zero, that we can make a claim. Maybe it's going to get to zero fast enough from both sides that eventually it will converge, and the series will converge as well. So there's two conditions that we need to look at to make sure that our alternating series will converge. So we have an alternating series. Remember, series is the whole sum. So if you look at the sequence of terms, so you remove the -1 to the n, right? If the sequence of terms, take a look, what does this mean? The new term, the next term is smaller than the previous term. So it's decreasing, right? So i.e., it's decreasing. And then the limit of, like, again, without the -1 to the n, the limit of the terms that goes to zero. So it's kind of like looking at an alternating sequence. We know that converges if its absolute value converges to zero. But now the series itself will converge to a sum. And again, we might not know what that sum is, but at least we know the series will converge if it's decreasing and the limit of just the terms, like without the -1 to the n, without the alternating piece, goes to zero. And then probably important to notice that, look, if one of the two conditions fails, it doesn't mean that it diverges. It just means that this particular test is inconclusive. Okay. And then we're going to talk about too, like, well, if it converges, is it converging like just based on the fact that it alternates? In other words, that's called a conditional convergence. It's converging with the condition that it continues to alternate, or would it converge regardless if it alternated or not? And so we'll find out that some alternating series only converge because it alternates. And if you take away the alternating part, aka trying to look at its absolute value, you'll see that it does in fact diverge. So, and wow, our first example. All right, so let's take a look. So if I right away recognize it's alternating, so that's great. And so there are two conditions to determine if it converges or not. So is it decreasing? So is the, like, if I look at the sequence 1 over n, is that sequence decreasing? And the answer is yes. So I'm going to say the sequence of terms decreases. I think in the homework, I even say, is the next term smaller than or equal to the current term? And yeah, that's another way to indicate that our sequence of terms is decreasing. Okay. Now, is the limit as n goes to infinity of 1 over n, does that equal 0? Yes, right. So we've satisfied both conditions. So we have a decreasing sequence of terms if you remove the alternating component, and we also have the terms going to 0. So then I can say, all right, thus the series converges. Thus our series n equals 1 to infinity of -1 to the n plus 1 of 1 over n converges by alternating series test. By alternating series test. Now, it doesn't, like right now, it's converging just on the condition that it's alternating. If we wanted to have a stronger conversion, we want to see, does it converge? Absolutely. And before I do that, I just want to address one thing in case you were wondering, why did you start with n plus 1? Honestly, it doesn't matter what you start with. It just is going to determine, is your first term going to be positive or is it going to be negative? So when n equals 1, our first term is actually a positive value. If it was just n, then first term would have been negative. So okay, so at least we do know, in fact, it converges, and at least it converges conditionally at the minimum. So how would we show that it converged absolutely? So to show that it converges absolutely, we'd have to consider this particular series, right? The series is n equals 1 to infinity of the absolute value of -1 to the n plus 1 of 1 over n, which is really the series n equals 1 to infinity of 1 over n. So if you look at it in absolute value, we have the harmonic series, or a p series where p is 1. It diverges, right? So I would say, okay, well, this diverges, right? Which diverges by a p-series test. So if the absolute component of it diverges, that means the series I was thinking about cannot converge absolutely. It only converges conditionally. So again, some of this is kind of just analysis. Like the directions may not have specifically said if it converges, determine if it converges conditionally or not. But that's something that we should think about when we have an alternating series. So I can say our series converges only conditionally. Converges only conditionally. And again, it's based on the condition that it alternates. And if it didn't alternate, then it would diverge. Okay. Now, I'm not really sure why I have D next. So I guess we'll go down. That is weird why I said D, then B, then I guess C. Weird. Okay. Okay, I tell you what, let's look at C right now, just because I think that's kind of interesting. Because here's another way that we can offer or show you an alternating series in disguise, right? So right now I don't see -1 to the n, but notice as you choose n equals 0, 1, 2, 3, because it's just integers in this case, natural numbers plus 0, you end up getting like cosine of 0, cosine of pi, cosine of 2 pi, cosine of 3 pi, cosine of 4 pi. And so if you think about, like on the unit circle, cosine of 0 is 1, cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1, cosine of 4 pi is 1, cosine of 5 pi is -1. So it's a sneaky way to make that an alternating series. So the only time I can ever use the alternating series test is if, in fact, you have an alternating series. So, if you don't see the -1 to the n, you can't use it. Or if you don't see a sneaky way to make it alternate, then you couldn't use it either. So I know this is an alternating series. So let's check. If you look, so you remove the alternating components and you just look at the sequence of terms square root of n plus 2. Remember, because we're removing the component that alternates. So does that sequence of terms decrease? And yeah, it does. If you make the denominator bigger, overall your function, your terms are getting smaller. So yes, I know that we have decreasing terms. Decreasing. I wanted to say decreases, and I wanted to write decreases, and I wrote decreasing terms. Let me just erase this. There we go. So it decreases. And then is the limit as n approaches infinity of, again, the part that's in not the alternating part, but the other component, the terms n plus 2. What is that as n goes to infinity? That equals 0. So you've satisfied both conditions to use the alternating series test. So I can say thus, our original series converges. Converges. Series, there it is. Converges by the alternating series test. Alternating series test. Okay, now that's just conditionally right now. It's converging because I have a condition that it alternates. But what if I consider the absolute value of the series to see if it converges absolutely? So let's so consider this series n equals 0 to infinity of, take out the alternating part, so here's the absolute value of it, right? 1 over n plus 2 in the root. Now, this is going to behave a lot like 1 over root n, which I know is going to diverge. So this one's going to also diverge. Now, if we have like if I know that, and this is just a good recap from comparison versus limit comparison. If I know that 1 over root n, like I know that 1 over root n. I keep thinking I'm picking the thinner marker, but there you go, double click it. We know that diverges, right? So the question is, how does 1 over the square root of n plus 2, is that bigger or is that smaller than this divergent sequence or series? And when you make your denominator bigger, overall it makes a fraction smaller. So I have something that's less than a divergent series, term for term. So I can't directly compare it, but I could do the limit comparison, right? So we could say, compare to this series, n equals, I'll start at 1 because I don't want to divide by 0, of 1 over root n, which diverges. I have a very, for some reason, a very slow lag time here with this drawing, which diverges by p-series tests. Okay, so then what we do is we're going to take the limit. So this is almost like a proof within a proof, right? So then the limit as n goes to infinity of 1 over root n plus 2 divided by 1 over root n, which equals the limit as n goes to infinity. So I would say just show me, right, just flip that, just show me one step. So 1 over root n plus 2 times square root of n over 1. That's going to be equal to 1, which is a finite number, so that the limit comparison test is going to confirm that our series will also diverge. So I could say thus, by limit comparison test, especially when I get over to the side here, I noticed that it's not as responsive. Maybe because I just need to restart my laptop or my tablet. Thus, by limit comparison test, our series also diverges. Boy, this is terrible. Our series also diverges. So what did that tell us? It told us that our original series, which alternated, only converges conditionally. It does not converge absolutely. So if it asked us to distinguish if it converges, does it converge just conditionally or is it absolutely? And I actually have seen that on the AP exam as a free response, where determine if this alternating series converges conditionally, absolutely, or does it diverge? Okay. Now, I think I'm gonna stop our video here. Hopefully, maybe reset my smartboard here so it responds a little bit better, and then I'll go through some more of the examples. I definitely want to go back through B and D, and then for the example number 2, it could be that you try those, and then I'll walk through them. But it could also be something where you just can fast forward to the end of the video just to see, hey, did you get the gist of that? Because once you understand the structure, what are you trying to do? What are you trying to prove? You just kind of go through that exact same process, just like we saw for limit comparison, just like we saw for the direct comparison test.